In the dawn of modern industrial computing, global enterprises faced an invisible architectural crisis that threatened to completely halt all computational progress long before the modern digital age even began. Early enterprise computing hardware platforms were entirely restricted to rigid, deterministic mathematical execution, rendering them fundamentally incapable of adapting to random pattern variances or processing unstructured corporate data streams natively. This systemic processing bottleneck forced early technology leaders to entirely reevaluate the core nature of calculation, moving far beyond binary constraints toward highly adaptive, self-correcting computational frameworks over time. According to documented historical frameworks from Cambridge University Press, the crucial conceptual bridge between organic biological neural systems and mechanical automation emerged directly from the specialized field of early cybernetics. Pioneer research teams realized that complex technology environments required continuous feedback loops to autonomously correct errors, mirroring how biological organisms maintain internal homeostatic stability amidst chaotic environmental shifts globally. This strategic structural pivot from static mathematical formulas to dynamic structural adjustments formed the absolute bedrock of artificial intelligence, introducing an engineering approach that redefined global information systems permanently. Instead of manually hard-coding every potential operational scenario into the physical machine, pioneering scientists began designing architectures that could alter their own internal execution paths using incoming informational data. The primary technical hurdle centered on modeling the intricate behavioral logic of a biological network using primitive electrical components, vacuum tubes, mechanical relays, and rudimentary magnetic core storage arrays. In 1943, Warren McCulloch and Walter Pitts published a groundbreaking mathematical framework demonstrating how simplified artificial neurons could calculate complex binary logical operations inside early experimental computers. Their abstract mathematical model successfully proved that combinations of basic binary switches could theoretically resolve any computable function, setting the long-term stage for modern decentralized enterprise computing layouts. However, this early network abstraction possessed a severe architectural limitation, because the critical threshold weights regulating the operational network had to be completely manually calculated by human engineering teams. The initial system completely lacked an autonomous learning mechanism to self-correct from execution errors, rendering it highly inefficient for large-scale corporate deployments where real-world data patterns drifted constantly. To resolve this structural bottleneck, Frank Rosenblatt introduced the definitive Perceptron blueprint in 1957, representing the first functional hardware implementation of an adaptive artificial neural network topology. Rosenblatt's design shifted corporate technology strategies away from manual programming methods, implementing an algorithmic process where the machine itself calculated and adjusted internal weights using linear discriminant functions. This historic architectural pivot deployed linear discriminant functions and simple multi-contact weight adjustment algorithms modeled directly after basic biological networks to allow autonomous data processing across scalable systems. By utilizing a built-in automated error correction loop, the early Perceptron could systematically learn how to classify binary input vectors, opening a clear path toward handling unformatted business datasets. The physical hardware execution of this system was successfully realized through the Mark I Perceptron, a massive analog computing platform constructed using custom motor-driven potentiometers for matrix optimization. These specialized motorized potentiometers function directly as the physical weights of the network, automatically turning to adjust electrical conductance values based on the feedback signals received during training cycles. The processing system calculated the variance between the actual output and target output, sending an electrical impulse back through the circuits to physically rotate the internal gears to minimize error. This precise mechanical implementation proved that statistical weighting networks could replace manual procedural rules, a profound revelation that altered the trajectory of automated data interpretation across enterprise environments forever. From a clear macroeconomic perspective, this shift laid the framework for replacing manual, procedural engineering rules with automated statistical weighting systems, optimizing long-term corporate infrastructure total cost of ownership. The business implications were massive as industrial organizations realized that computing platforms could autonomously refine output precision without requiring continuous, expensive manual software rewrites by specialized engineering teams. This early technological transition triggered a significant workforce shift, fundamentally altering the required competencies, core technical attributes, and skill sets expected of early system developers and corporate engineering departments. Instead of focusing purely on rigid deterministic logic trees, programmers had to master statistical variance, probability theory, matrix interactions, and mathematical optimization parameters to manage adaptive learning infrastructures. Corporate technology financial models began incorporating active training cycles, hardware degradation matrices, and data curation metrics alongside traditional development costs, redefining international information technology budget allocations completely. Research evaluations from the Carnegie Mellon University AI repository confirm that the fundamental optimization patterns discovered in this historical era established the core equations utilized across modern language models. Enterprise executives realized that the capability to automate complex pattern recognition was the ultimate strategic differentiator, transforming disorganized business records into highly structured, actionable competitive intelligence assets globally. The deployment lifecycle for modern intelligent systems dictates that engineering teams must begin by isolating simple linear classifications before attempting to manage highly convoluted, multi-layered data structures at scale. Tracking these historical thresholds systematically proves that continuous weighting arrays are the absolute native prerequisite for scaling computational intelligence to achieve true automation across modern global corporate platforms. Without this conceptual evolution from hard-coded hardware circuits to variable, self-adjusting weight matrices, modern large language models, autonomous agentic workflows, and high-density vector databases would be completely impossible to develop. Let us now analyze the exact mathematical formulation of Rosenblatt's historical network to understand its mechanical limitations and why it served as an essential milestone for software engineering. The perceptron operates by calculating the dot product of an incoming data vector and its internal weight matrix, generating a single scalar value passed directly through an activation function. If the computed product exceeds a predefined numeric threshold boundary, the artificial neuron fires an output signal of 1. Otherwise, it defaults to 0, creating a binary classification line. This mathematical boundary strictly limits the basic architecture to linearly separable problems, meaning the corporate processing system can only divide data groups that can be split by a straight line. While this configuration worked perfectly for simple logical operations like AND or OR, it completely failed when presented with nonlinear patterns, such as the exclusive OR matrix function. This mathematical ceiling eventually triggered severe criticism from contemporary academic rivals, stalling industrial research funding for years until multi-layered networks were developed decades later to handle complex data matrices. Despite these inherent structural limitations, the fundamental rule of updating weights based on output error remains the absolute foundation of backpropagation algorithms used in the most advanced modern models. The early cybernetic researchers effectively proved that an enterprise technology architecture does not require hard-coded logic if it contains an algorithmic mechanism capable of iteratively minimizing error over time. This profound architectural insight shifted the entire technical industry away from rigid procedural code towards statistical learning systems, laying the physical infrastructure foundations for modern enterprise data frameworks globally. When we evaluate legacy business platforms and modernized cloud environments today, we see the direct lineage of these continuous weighting mechanisms managing unstructured corporate knowledge repositories completely seamlessly. Industrial modernization requires a deep strategic appreciation of these historical milestones to prevent current software architects from repeating past mistakes regarding algorithmic scaling and infrastructure optimization choices at scale. The historic transition from manual rule validation to automated statistical learning transformed early cybernetics from an abstract academic theory into a highly practical tool for data automation and transformation. As global commercial markets became increasingly dependent on automated systems, the demand for stable algorithmic frameworks accelerated rapidly, forcing corporate institutions to invest heavily in advanced computational logic development. By closely analyzing the constraints of the first perceptrons, modern enterprise technology teams can better appreciate the massive scalability of current neural architectures and deep transformer token arrays. The mechanical simplicity of Rosenblatt's design highlights a critical technical truth. Scaling intelligence requires robust hardware layers capable of executing massive parallel weight adjustments with low operational latency. Early computing hardware platforms clearly proved that without highly flexible information structures, modern enterprise architectures remain completely vulnerable to rigid logic failures when processing volatile business data patterns. This clear historical lens allows corporate chief technology officers to separate artificial marketing hype from true architectural innovation, ensuring enterprise resources are allocated exclusively to scientifically verified computing architectures. The initial shift toward statistical intelligence also introduced new cybersecurity paradigms, as early engineers realized that malicious data manipulation could completely alter the learning path of an automated system. Securing the underlying data pipeline became just as critical as protecting the machine code, a core structural principle that remains central to modern zero-trust frameworks and secure database deployments. By thoroughly understanding how primitive networks were vulnerable to operational noise, modern security architects can design better defenses against contemporary adversarial attacks and sophisticated indirect prompt injection methodologies. The ongoing evolution of computational logic is a story of continuous optimization, moving from vacuum tubes to silicon microchips while retaining the core mathematical principles of algorithmic adaptation. Every modern agentic workflow and automated retrieval pipeline relies on the same basic premise established during the early cybernetics era. Information context must actively guide internal system corrections. As global enterprises continue to deploy generative models, grounding technical strategies in historical computer science ensures a completely stable transition away from legacy, rigid operational software methodologies permanently. The valuable architectural lessons of the 1950s serve as an engineering compass for modern developers, proving that simple components generate complex intelligence when properly networked together systematically. By systematically isolating linear functions first, early computing engineers established the foundational building blocks that allowed future generations to successfully construct deep, multi-layered neural systems for enterprise use. This profound historical continuity highlights why understanding the origins of artificial intelligence remains absolutely necessary for any technology leader aiming to build scalable, resilient corporate software platforms in 2026. Computational logic is no longer a theoretical academic pursuit, but the core engine of enterprise corporate productivity, digital transformation, and systemic innovation across all modern global corporate networks. As we step into the next era of enterprise intelligence, we build directly upon the mechanical brilliance of the engineering pioneers who redefined the physical limits of calculation. The ultimate blueprint of enterprise intelligence requires a clear understanding of where we started to effectively navigate where the modern cognitive infrastructure architecture is going in the future. Stop guessing your tech strategy and wasting your time. Subscribe to Enterprise Tech Brief right now. We deliver zero hype, pure architecture, the blueprint of enterprise intelligence, completely free. Hit the subscribe button.